6a, the standard normal curve. So we've talked about normal distributions. In fact, we said that the normal distribution was defined by the mean and the standard deviation. So mu and sigma define a normal distribution. When we talk about a standard normal distribution or a standard normal curve, it means that we have a set value that we're going to use. If you think of standards, they're something that's regulated and set. Standards are things that you have to follow. You have to do things a certain way. Or if you deal with high jumping, pole vaulting, what they put that bar on is called the standard. And it allows you to have exact heights, 5 feet 6 inches, 7 feet 2 inches, right? So you have these standards, or standards something you compare against. So when we're talking about a standard normal distribution, we're talking about a distribution where the mean is equal to 0 and the standard deviation is equal to 1. So it's a very specific normal distribution where the mean is 0 and the standard deviation is equal to 1. Now remember that any normal distribution is symmetric. The center is the mean, the median, and the mode. That the area under the curve is equal to 1, right? The total area underneath the curve is equal to 1. Half of that being on the right side of the mean, half of that being on the left side of the mean. That if you go over one standard deviation, mu plus sigma, that you're at the inflection point, and we can actually get into the empirical rule too, that within one standard deviation, the mean is 68% of the data. Within 2 standard deviations, the mean, 95% of the data. Within 3 standard deviations, the mean, 99.7% of the data. Okay, so that all follows. But with a normal distribution, we say let the mean be equal to 0 and the standard deviation be equal to 1. Right, and 68% of the data is within 1 standard deviation, 95% within 2 standard deviations, 99.3% within 3 standard deviations. So we're basically doing a very simplified form of a normal distribution. Now the reason we do this is because it allows us to start comparing different distributions and to start determining areas underneath this curve other than exactly 1 standard deviation away. Now, the way that we're going to do this is we're going to use a table. And we're going to use that table to determine what the area is underneath the curve at up to and including a certain point. The problem with using a table is that, remember, every normal distribution would have to have a different table depending on the mean and the standard deviation. So thus we come up with the normal distribution, the standard normal distribution, where we have a mean of 0 and a standard deviation of 1. So the question is, how do we get that if we start out with any distribution? And simply put, we standardize it using the z-score or standard score. So if you remember, when we talked about measures of position, we talked about the z-score or the standard score. Z was equal to x minus mu over sigma. And if we think about what that does, let's start out with a mean and a standard deviation. So I'm going to get rid of this. And apply this z-score. What if I have a mean of 100? So we're going to deal with IQs just because it's an easy way to show this. If I have a mean of 100 and a standard deviation of 15, then I can create this. And remember, we did this when dealing with the empirical rule or dealing with Chebyshev's inequality. So I can say the mean of this is 100. If I come one standard deviation above, it's 115. Another standard deviation 130. Another standard deviation 145. Going back the other way, minus 15 gives us 85, 70, and 55. So now I'm going to apply this z-score or standard normal score to each of these values. So the first thing it says is take the data value and subtract the mean. The mean is 100. So 100, I'm going to switch colors here. 100 minus 100 is 0. 115 minus 100 is 15. 130 minus 100, 30. 145 minus 100, 45. And going the other direction, negative 15, negative 30, negative 45. Now, first of all, we can see right here that I already transformed this or moved this so that now my mean is 0. Now, if I divide by the standard deviation, my standard deviation is 15. 0 divided by 15, I'm going to switch colors again. 0 divided by 15 is 0. 0 divided by any number is 0. So we got 0. 15 divided by 15 is 1. 30 divided by 15 is 2. 45 divided by 15 is 3. Negative 15 divided by 15, negative 1. Negative 2, negative 3. And we can see that we now have a standard deviation of 1. So we transformed this distribution into a distribution where the mean is equal to 0 and the standard deviation is 1, thus making it the standard normal distribution. So a standard normal distribution. Which means that now instead of having to have a whole book of tables for all these different distributions, all we need is one distribution that deals with a mean of 0 and a standard deviation of 1, one table that does that, and then we can use z-scores to convert any distribution to that. And that allows us to compare two completely different things. And we used this initially when I brought it up to compare the height of a male versus the height of a female, even though the average heights and the standard deviations were different. So let's get into this table, what it looks like and how it works. So first of all, I have a copy of the table here. So the table is two-sided. If I come in a little bit, maybe you can see standard normal cumulative probability table. And notice that, that there's a little picture of a normal distribution here, and that picture has the left-hand side colored in. If I swap to the back of the table, we see that it continues on, but now we have more of that area colored in. Now this table is available in Blackboard as one that you can use. You are expected to use this and you need to know how to use it. Okay? And what I'm going to show here is the basics of how to use a table like this. First of all, we will see that this table, and remember it has two sides to it, so we see that it shows z up here. That's the z-score. And at the top you'll see 0.00, 0.01, 0.02, 0.03, continuing on until you get to 0.09. So it shows all that across the top. Along the side it says negative 3.7 or less. And we're on page 1 of the table. There's two sides to this table, so the first side and the back side. First side, these will all be negative numbers. The back side, they'll all be positive numbers. So negative 3.7, negative 3.6, negative 3.5, negative 3.4, negative 3.3, negative 3.2, negative 3.1, negative 3.0, negative 2.9, negative 2.8, negative 2.7, negative 2.6, dot, 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 all the way down to negative 0.0. It doesn't show a negative here because unfortunately 0.0 is not positive or negative, but we can treat it as there's a negatives there. So what happens with this is we can take a z-score with 2 decimal places. And we can look it up in this table by using these row headers and column headers. So let's say I have a z-score of negative 2.73. What I'm going to do is I'm going to come down here, and this row right here, these row headers, sorry, that column there, and its row headers, give you the sign, the ones place, and the tenths place. So this right here is going to deal with this. It's going to take that. Up here, these column headers, notice that it's all 0.0 and then followed by numbers, 0, 1, 2, 3, right? The hundredths place is shown there. So this hundredths place is going to end up over there. So if I want to look up negative 2.73, I'm going to look here for negative 2.7, and I'm going to look up here for 0.03, negative 2.73. I can then go across and come down from those, and I'm going to find some value. That value, in this case, negative 2.73, gives me 0.0032. So 0.0032. So that's the value. Now remember, in the upper right hand corner of this table, there was this little drawing, looked a little like that, showing us that this value here is the area to the left of that z-score. So this is called the cumulative, standard normal cumulative probability table. Cumulative, remember, is where you're adding it up, everything up to a certain point. Remember our cumulative frequency? Same thing here. So this is giving us the area to the left of that z-score. In this case, 0.0032. Well, this area also relates to probability. Remember, the area underneath the curve, under the whole curve, is 1. And then if we have z-scores, areas at certain points can be anywhere from 0 to 1. Probabilities are always between 0 and 1. So if my area to the left of that z-score is 0.0032, then my probability of randomly selecting something that is less than that z-score is 0.0032. So that's not just an area, that's a probability. The probability of something being in that little range up to that z-score is equal to the area up to that z-score. And that's what's kind of cool about this, is now we can say, okay, if we have a z-score, we can find the probability that something is less than that z-score. Let's grab another one, just because we can. I'm going to modify this slightly. I'm going to come up here a little bit, do this, and say, what if I want, we can get this one out of here too. z is equal to negative 1.62. So z is equal to negative 1.62. Well, then what I'm going to do is I'm going to come down the table until I get to negative 1.6. Right, saving myself some time just writing that in there. And I'm going to go over, and then I need to get to 0.02. And I'm going to get some values. So negative 1.62, I look in my table and I get 0.0526. 0.0526 is what it shows in my table. So now the area to the left of this z-score is 0.0526, or the probability that I randomly select something that has a z-score less than that is 0.0526. And it doesn't matter what my normal distribution is. Once I normalize it by finding the z-scores and turn it into this, then when I have a z-score of negative 1.62, 0.0526 will be the area to the left of that, or the probability of randomly selecting something less than that will be 0.0526. Well, that leads to another possibility. What if I want the probability that it's more than that value? Then isn't that looking at the area to the right? Well, that's just the complement. So if I want the probability that I get a value greater than, so I'm going to say z greater than negative 1.62, I'm going to take 1 and subtract this 0.0526. And if I subtract 0.0526 from 1, then I get 0.9474. 0.9474, so just 1 minus 0.0526. So we can find the probability that the area, that it's going to be in the right-hand side, that it's going to be greater than that. Okay, so that's really handy for us to be able to do and to be able to use this table to do it. Okay, remember cumulative probabilities are always going to be between 0 and 1. And the area underneath the table is always going to be between 0 and 1. This only can be used for finding a cumulative probability. I cannot use this table to determine the probability that z is equal to negative 1. And the reason I can't do that is because if I have z equal to an exact value, then I'm going to get a line. If it's an exact value, it's going to have no width. It's just going to be the line. And what's the area of a line? Well, if it has no width, that's 0 times the height. Any number times 0 is 0. So you find no area. So we can't use this table to find the probability that something is going to be equal to a value. We can find the probability that it's less than. We can find the probability that it's greater than. And realize too, since equal to has an area of 0, then if we ask the probability that it's less than, or the probability that it's less than or equal to, they're going to give the same value because the equal to part is just 0. So we can use these to pull it together. Let's do a couple examples here with these z-scores in finding the probability that the z-score is in a certain range, or less than a certain value, greater than a certain value. Let me get rid of this red marker and go back to a black one. I want to find the probability that z is greater than 2.19. Probability that z is greater than 2.19. So what I'm going to do is I'm going to go to my table. So I've got my table, and I'm going to go to, this is a positive number, first of all, so I'm going to go to the positive side, the second side of it, all my numbers are positive. And I've got 2.19, so I'm looking for 2.1 and 0.09, right, on my table there. And if I do that, 2.19, 2.1, work my way across to 9, 0.9857. Just let me do a double check, 0.9857. 0.9857. So I pull that out of my table, 2.1 in the left-hand column, 0.09 at the top, find where they match, 0.9857. So I got 0.9857. And I'm looking for the probability that z is greater than 2.19. Remember my table, and it's got that picture to remind me, always gives me the area to the left. I'm looking for the greater than, so I'm looking for the area to the right. So I'm going to subtract it from 1 minus 0.9857, which gives me 0.0143. So the probability that we have a z-score that's greater than 2.19 is equal to 0.0143. We looked up the 2.19 in the table, found its value, and since we're looking for the probability that it's greater than, we subtracted it from 1, and that gave us the probability that it was greater than that amount. Now, what we may have happen to us is we may get asked a question of, what's the probability that it's between two values? Because less than is easy, we just pull the number off the table, and that's the probability that it's less than. Greater than, we subtract it, we pull the number off the table, subtract it from 1. In between, we do something a little bit different. So I want to know what's the probability that z is between negative 1.28 and positive 0.63. So I want it in this range between negative 1.28. Let me just draw that a little more clear on my monitor. It's not showing up as easily to me. Negative 2.18. Hopefully that's a little more readable. I can read that, okay? And let me make it so you can see the z. There we go. So negative 2.18 is less than z is less than 0.63, so we're looking for z to be between those two values. So the first thing I'm going to do is I'm going to look up negative 2.18 in my table, which means I'm on the negative side again. Negative 2.18 gives me 0.0146. 0.0146. That's z of negative, that's with z equal to negative 2.18. I'm also going to look up 0.63, so that's on the positive side. So 0.6, go down to 0.6 over to 0.03, gives me 0.7357. 0.7357. So now what I have is I have this, and it's not a bad idea to draw it so we know what we're looking at. I have a z-score of negative 2.18 and a z-score of 0.63. The area to the left of negative 2.18 is 0.0146. The area to the left of 0.63 is 0.7357. I want to find the area between them. Now, simply stated, the area between them is just the difference. Right now, I am standing approximately 1 foot away from the wall, and the camera is approximately 4 feet away from the wall. How far am I away from the camera? Well, if I'm 1 foot away from the wall and the camera is 4 feet away from the wall, then 4 minus 1 says the camera is 3 feet away from me. Right? And that's the same idea here. I have the area to the left of this first value. I have the area to the left of the other value. The difference of those two areas is going to be that center area. So I'm just going to take this as 0.7357 minus 0.0146, which is going to give me 0.3211. So the probability of randomly selecting a z-score between negative 2.18 and 0.63 is 0.3211. Or we got about a 32% chance. Now that's good, that allows us to work with this, but now let's take this into the real world. Because that's great, we can find these given a z-score, but let's look at a real world problem. I'm going to put down my table for a moment. I'll be picking it up again in just a little bit. Well, let's get this out of the way and look at a real world problem. For the fun of it, I'm going to look at IQs. We've dealt with it before. We know that the population of IQs has a mean of 100 with a standard deviation of 15. And I want to find out if I randomly select a person from the population, what is the probability that their IQ will be less than 95. So we know that the population mean is 100, standard deviation is 15. And I want to find what's the probability that I randomly select a person from the population and their IQ is less than 95. So how do I do that? Well, I use my z-score. So the first thing I'm going to do is I'm going to say z is equal to x is 95. I'm trying to use that real world value of 95. So 95 minus the mean of 100 over the standard deviation of 15. 95 minus 100 gives me negative 5 over 15. If I convert that to a decimal, I get negative 0.3 repeating. Now we're finding the z-score. We're going to end up using our table, and we know that our table only deals with z-scores to 2 decimal places. So we're going to round z-scores to 2 decimal places, so negative 0.33. Because if that's a 3 repeating, it's 3's continuing, and that's going to round it to 3. So negative 0.33. Now that I have that, I have my z-score, now I can go to my table. So I grab that table again, and I'm at negative 0.33, so negative 0.3, get onto the right side of the table. Negative 0.3, and I come over to 0.03, and I get 0.3707. 0.3707. Had to look back at my table here. So 0.3707. And remember, our table always deals with the area to the left. We want the probability that the IQ is less than 95, so we're dealing with the area to the left. So the probability that we randomly select a person with an IQ less than 95 is 0.3707. So note, this all has to do with your ability to read the table. If you can find a z-score, and then look up that z-score on the table, then you just have to know, are we looking for the area to the left? Are we looking for the area to the right? Are we looking for the area in between? We find it, and that becomes the result. The probability that we find someone with an IQ that's less than 95. Well, let's stick with the same type of thing, but modify the question a little bit. So I'm still going to deal with IQs, but I'm going to say, what's the probability that we randomly select, and I didn't leave that P there, a person with an IQ between 112 and 117. So I don't know, what's the probability that I randomly select a person whose IQ is between 112 and 117? So I'm going to need to find two z-scores. I'm going to find z of 112, which is 112 minus 100 divided by 15. That's 12 divided by 15, which reduces to 4/5, or 0.8, and I'm going to put this extra 0 in there. Now you may wonder, why did I put that extra 0 in there? Remember, the table deals with 2 decimal places. So I want 0.80, I want 2 decimal places. Even if it only came out to 1, let's give it 2, because that's what the table is going to look for. And now I'm going to find z of 117 is equal to 117 minus 100 over 15 is equal to 17 over 15. So that's 1 and 2/15, right? So it's going to give me 1 point. Well, what's 2/15? So 17 divided by 15 gives me 0.13 repeating. So 0.13 when I round it, because if I'm continuing with 3s, that's going to round to a 3. So 1.13. So now that I have those z-scores, I can now look them up in my table. So I'm looking for 0.80, or on the positive side, 0.8, and then 0.00 from the top gives us 0.7881, 0.7881. That's the area to the left of 0.80. And then 1.13, so 1.1 and 0.003 gives me 0.8708. 0.8708. So that's the area to the left of the other one. So essentially we're looking at this. An area here of 0.7881. Right? An area, and actually I should put that further over, right? And then an area there of 0.8708. So we're going to take 0.8708, 0.8708, and subtract 0.7881. Right? So just to make sure I don't do any stupid calculations in my head, 0.8708, 0.7881, and when we subtract, if we hit the right digits, we get 0.8708. I had a decimal in there accidentally, and 0.7881. We get 0.0827. So the probability that we randomly select a person from the population with an IQ between 112 and 117 is 0.0827, or just over 8% of the population will have an IQ between 112 and 117. So that's the start of working with a standard normal distribution table and finding cumulative probabilities, the probability that a value is less than a certain amount, greater than a certain amount, or in between two values.